Dear friends, welcome back. So, in our previous lecture we finished a preliminary approach for wing planform geometry selection, where the driving factors are CL design, right, which depends upon the wing loading, right. So, CL design from the level flight conditions, it is twice depends upon 2 times W by S upon density at that particular flight altitude times v square, right, flight velocity square. So, from the we observed for a given flight velocity or the mission requirement, we with the variation of W by S, there is a variation of CL design, right. So, based upon this CL design, we have proceeded ahead and this W by S and with some non-dimensional parameters as an input such as aspect ratio and taper ratio, we figured out how to estimate the wing planform geometry in terms of span of the UAV, right, which is aspect ratio times area, where area you got S is from W upon wing loading W by S, which you have considered as an input, right, variable of the iteration. And then using this S here, you figured out what is the span for a given aspect ratio, and then with the input of lambda taper ratio, you got what is the root chord, what should be the root chord to achieve that area with the span, with that particular span, right, which means this is equals to 2S upon B times 1 plus lambda. So, lambda is input here, okay. And then you figured out what is CT based upon lambda, which is CR times CR times lambda, right. So, with that we estimated what should be the wing planform area, right. So, but CL design ideally depends upon, so planform area governs the total force here, isn't it, but the cross sectional properties governs this particular CL. We need certain CL design for a given wing planform area and the weight of the UAV, which more or less we can say this CL design depends upon this wing loading, and this CL design is governed by the cross sectional properties of the wing, right, isn't it. The force is governed by S here, planform area, lifting area, and now with that lifting area and lifting area and then say the dynamic pressure, you are now having CL value, isn't it. So, the CL factor varies from what 0 to say typically 1.2, 1.3 near stall. So, more or less when you operate at certain angle of attack where the CL is within less than 1. So, it is actually decreasing the overall lift that it will generate, isn't it. Half rho v square S itself is a lift, or say it is a force, multiplied this by this non-dimensional term, right, will talk about the total lift generated, right. So, this CL is governed by the cross sectional properties. Now, like in the current lecture, we are going to discuss about what should be CL alpha for the wing and CL and alpha trim. So, in order to achieve this CL, what we call it as CL design, right, we need to talk in terms of what should be CL alpha of the planform, right, or say CL naught of the planform, or say alpha at which CL is equals to 0, or alpha, or say definitely and instead of or we should use and. Here any CL naught or alpha at which CL is equals to 0, anything is sufficient, right, either this or this, CL naught or alpha at which CL is equals to 0 and alpha design, right, which corresponds to CL design here, right, isn't it or not. Do you remember this formulation? So, we assumed a linear variation of CL with alpha till certain domain, right. After that there will be nonlinear variation near stall, there is a loss in lift, right. So, within a linear regime, so what we have is alpha at which CL is 0, this we discussed many times, right. Say if I am, so let us say this is my CL design corresponds to CLD, and this corresponding alpha at which I can achieve this CL design is alpha d, right. So, using the definition of slope, CL alpha of this wing, entire wing should be or say CL design minus CL at which alpha at which CL is 0 is the CL at alpha at which CL 0 is 0, isn't it, upon alpha design minus alpha at which CL is equals to 0. So, CL design is equals to CL alpha times alpha d minus alpha at which CL is 0, isn't it? Am I correct or not? So, that means if I have to talk about this CL design, I need to talk about CL alpha, which is again the cross sectional property of the wing. Say, let us say there is a wing here that is giving you the lift, desired lift, right. So, say this is the wing that you have designed, it is giving you the desired lift, right. So, but the cross section is what is going to, the wing area is going to help you with this half rho v square, yes, right, but the cross section is what is going to help you with the corresponding CL design. So, when you talk about cross section, that means you need to talk about CL alpha, right, CL alpha of the entire wing, and then finally the entire wing is made out of cross section at each and every location, right. That means you need to know what should be the profile that you need to select for that particular wing. To be frank, what should be the aerofoil that you need to select, right. How can you select that aerofoil? By knowing what should be the corresponding aerodynamic characteristics of a particular aerofoil. Now, say if you get what should be, so in order to generate the CL design, what should be the 3-dimensional CL alpha, right, and alpha design as well as alpha at which CL is 0. If you know those parameters, then you can convert them to 2-dimensional profile. What should be CL alpha 2D based upon 3D data, right, and the wing planform geometry in terms of aspect ratio and E. You can use those values to find out what should be the corresponding CL 2D here, right, isn't it. So, for example, see this from aerofoil to aerofoil, this particular the same CL design can be achieved at different alpha d. Am I correct or not? Alpha design. If you select a particular aerofoil, it has a particular alpha at which CL is equals to 0, which we thought more or less constant for wing as well as airfoil, right, and alpha design for wing will be different as well as aerofoil is different, right. So, but for the time being we assume both are more or less same, right. Otherwise, alpha design we will say it is possible at a particular angle of attack, right, 3-dimensional angle of attack. From there you find out what is alpha at which CL is equals to 0, vary alpha at which CL is equals to 0 for those, for a given alpha design, right. By doing so, what happens is the CL alpha varies, because you know CL design, you have fixed alpha design, right, you make these two as a variables of the iteration. So, you can find out the corresponding CL alpha, isn't it. Once you know CL alpha 3D, you can find out what is CL alpha 2D, because you know what is aspect ratio and you know what is E based upon the previous what you call discussion, right. We have developed this previous subroutine based upon for the planform selection. So, there from there you figured out what is the aspect ratio and what is the E, right. Then using those two values as an input here, you can find out CL alpha 2D. So, to be frank, it is like CL alpha 3D is equals to CL design upon alpha d minus alpha at which CL is equals to 0, right. So, this is same for aerofoil as well as wing, isn't it. So, depending upon this we can find out what is CL alpha 2D, right. What is CL alpha 2D? Yeah, CL alpha 3D upon 1 minus CL alpha 3D upon pi E AR. So, we know what is E, what is AR, right. You can find out what is CL alpha 2D from there, fine. Once you know like CL alpha 2D, you know you can find out based upon this alpha at which CL is equals to 0, you can find out CL naught 2D. CL naught 2D is equals to minus of CL alpha 2D times alpha at which CL is equals to 0. The CL alpha 2D is equals to minus CL alpha CL naught 2D is minus CL alpha 2D times alpha at which CL is equals to 0, right. So, you can find out 2D as well as here, from here you can also find out what is 3D CL naught required. CL naught required is like CL alpha 3D times alpha at which CL is equals to 0, isn't it, minus of, okay. So, once you know CL naught, what should be the 2D CL naught, what should be the 2D CL alpha, and what should be alpha at which CL is equals to 0, 2D again, right, 2D and 3D are same. So, then you will be more or less getting that you will be able to find out what should be the corresponding aerofoil from the aerofoil database, right. So, that is how you can select the aerofoil here. Okay. Fine. So, let us now write an algorithm to do this. So, it is a new script again. So, what we have is CL underscore design, right. So, CL underscore design from our previous performance like wing plan form geometry, we will try to take data from there. So, at 2000 meters when flying at 30 meters per second with a weight of the UAV as 8.1 kg. So, with 0.4 taper ratio. So, what we have is E, right. So, let us now assume the aspect ratio as 10 for this particular case. Let us assume aspect ratio as 10. So, now I will try to take a new sheet here. Let us take aspect ratio 10. Let us take the data, corresponding data. So, the wing loading is, otherwise the weight of the UAV is 8.1 kg, S of the UAV is what? For aspect ratio 10, S is approximately 0.81 meter square. So, S is 0.81 because meter square. No, this is for wing loading of 10, not aspect ratio of 10. I am sorry, this is wing loading of 10. So, the wing load, so it is simply W upon W by S, it is 0.81 meter square, right. So, with this area and wing loading, by considering an aspect ratio, now the aspect ratio here varies from 4 to 10. So, for data 7 which corresponds to aspect ratio 10 and at wing loading 10 kg per meter square, and the wingspan is about 2.8, right, 2.84 meters, 2.84 meters, and the aspect ratio that we have considered here is 10, right, and the wing loading is also 10 from the data, 10 kg per meter square or 100 Newton per meter square approximately. So, and then what do I require essentially is this particular parameter CL design, right. So, CL design here is approximately, CL design is 2.2. Okay. So, let us consider this as an input here. So, for me to calculate 0.22, not 2.2, 0.22. Okay. 0.22, yeah. So, the CL design from here is 0.216, which is 0.22, this is 0.22 that we have considered. So, CL design is 0.22. So, the value of K for this particular aspect ratio and CL aspect ratio. So, for aspect ratio 10, the value of K is, so the 7th value is 0.0421. So, the value of K is 0.0421, right, and where E, otherwise you can say since aspect ratio is 10, we can also do this way, aspect ratio is 10 and Ostwald's efficiency factor for this aspect ratio is 0.7566, 0.76. Okay. So, considering that E is 0.76, so K can be 1 by pi 1 upon pi E AR, right. So, These are done. Now what we need to do is we have to vary this. We need to find out what is CL alpha 3D, right? CL alpha. This capital letters CL here talks about 3-dimensional case. Right. CL alpha is equals to CL design upon CL design upon AOA underscore design, right, minus AOA underscore 0 CL, okay, 0 CL. And let me define these variables used. So, this is lift curve slope, it is 3D. So, we need to vary these values, angle of attack as well as design angle of attack and then angle of attack at 0 lift, right. So, first of all I would like to vary these two parameters, AOA underscore design angle of attack, right. If it varies from say 2 degrees or say 1 degree, right, 1 okay, 1 star pi by 180. So, varies from 1 degree with an increment of 0.5 degree pi by 180 up to 5 degrees, let us say. So, you have data for about 10 points here, right. So, pi by 180. Instead of 0.5, let me take it up, make it 5, sorry 1 degree, right. Yeah, you can choose the like interval just to minimize the plotting time. I would like to use it as one step of 1. You can choose it to be 0.5 or less than that, even less than that. Okay. So, this is how typical design angle of attack, within this range, because even that, yeah, L by D maximum for typical airfoils will also fall within this range, maybe up to 7 degrees, you can say, yeah, maybe up to 7 degrees. And CL alpha from here is like depends upon AOA, right, and then alpha at what CL is equals to 0. So, if this varies, let us say for AOA underscore 0 lift coefficient, right, or sorry, angle of attack at which lift is 0 is from say minus 0.5 degrees to with an increment of 0.5 degree with an increment of minus 0.5 degree. So, it should be minus 0.5 or 0.5, right. It should be from varying some say 0.4 degree, right. So, minus 4 degree, say pi by 180 with an increment of 1 degree. So, I am trying to convert this degree to radian here. So, this is pi by 180. So, up to say up to 0 degrees, let us do that, up to symmetric airfoil, let us say. So, this times pi by 180. This is in general from 2 degrees, right, 2 degrees or 3 degrees at least design angle of attack, otherwise there is no use, right, we can't use effectively use the CL, maybe from 3 degrees to be frank, from 3 degrees. So, that makes sense. So, let me introduce the variables of this iteration. So, from j is equals to j plus 1, sorry, j is equals to 0. So, it becomes what, j is equals to j plus 1 here inside this loop. So, I would like to store angle of attack design of j comma 1 is equals to AOA underscore D multiplied by pi by 180 by pi. I am storing it in terms of degrees again, pi by 180 by pi, right. So, it is done AOA design, and then so we have CL alpha 3D, right, isn't it? So, let us have another variable for the inner loop. So, CL alpha here depends upon both, no, alpha design as AOAD as well as AOA at which CL is 0. So, I would like to store the second variable as well, AOA at which 0 CL, right, 0 lift coefficient. So, which is again there I can simply store it as a single column vector, or say I can repeat storing for each and every iteration, outer loop iteration as well. So, this is equals to AOA underscore 0 CL times 180 pi 180 by pi. So, converting it to radians again. So, 0 lift angle of attack in radians. Okay. So, similarly design angle of attack in radians. Design angle of attack in radians. Okay. CL design is what we need to produce, right, isn't it? When moving at 30 meters per second, we need to produce the CL design. So, with a wing of aspect ratio 10. So, S we are not using it anyway here. So, weight of the UAV capital W is 8.1 times 9.81. Okay. S of UAV is 0.81 because as we considered for wing loading 10 here. And then what do we need? So, CL alpha is known. So, CL alpha 2D, okay. CL, so let us make it small letters, CL underscore alpha. So, talks about 2D case. So, this is like CL alpha 3D for that particular iteration upon 1 minus CL alpha 3D upon pi E AR. Okay. So, airfoil lift curve slope, which is 2D, right, and then we need to know what should be CL naught capital. So, capital CL naught we can, yeah, capital CL naught CL naught is equals to CL alpha 3D minus of CL alpha 3D times alpha at which CL is 0, right. Okay. So, lift coefficient at 0 alpha. For wing, right. So, we need to now talk about lift coefficient at 0 alpha for airfoil. So, the second depends upon CL alpha 2D times the same angle of attack, right, because we considered that as a decent assumption. It's 0 lift, there is no induced angle of attack, that is what we assume. So, it will be more or less same. So, what we have is lift coefficient or 0 lift coefficient airfoil 0 lift coefficient. Okay. Right. So, airfoil, let us make this as airfoil underscore airfoil selection. Okay. So, now another important aspect is, like, once you select this, you should also look at that design CL, are you able to achieve that particular L by D that you have considered, right. That is another aspect that you need to take care of. I am not going to include that particular aspect here, right. So, figure 1, what I am trying to plot right now is, so for different design angle of angle of attack design, which is nothing but trim angle of attack for that particular design CL, right. So, for different values of this or say for different values of 0 lift angle of attack, how this CL alpha is varying and CL alpha 3D 2D as well as CL naught 3D 2D, right, for wing and airfoil. At the same time, we will cross plot or superimpose, not cross plot, superimpose when there is a change in design angle of attack, what will be the variation of these parameters with again AOA at CL is 0. Okay. Subplot mainly with four parameters, right. So, let us talk about only 4, rest if you are interested you can consider them plotting. So, what I am interested right now is in plotting for angle of attack for 0 CL, right. So, 0 CL, that will remain constant colon comma 1. So, that I am plotting for various design trim angle of attacks. So, what I have is, so I am plotting the variation of CL colon comma 1. So, this corresponds to when alpha is 3 degree, design alpha is 3 degree or alpha trim is 3 degree for design CL, right. So, I can say I can connect them with the same K colon K star. So, okay. And then, so I have to hold it on because this varies and this varies for various design angle of attacks, right, that we have considered. So, this can be B black. So, for 3 degrees, 4 degrees, 5 degrees this one, right, for 5 degrees, this is for 6 degrees of alpha design, right, and then we varied it from 3 to 7 degrees. So, K, B, G, M, R let us say and then M, okay, control C, control V. So, this is for 5. So, 3, 4, 5, 6, 7 degrees. So, and the Y label is CL underscore backslash LPH alpha, right, in degrees. Sorry, per radian, CL alpha per radian, that is what you are going to get. Okay. So, this is 3 dimensional, CL alpha underscore 3D. Okay. So, I would like to plot for second one, which is instead of CL naught 3D, right, this is CL naught. So, what I can do is, okay, this is CL naught. So, this will be CL underscore naught 3D. The third plot will be CL alpha, right, small CL, isn't it? So, what we have is small CL, right. So, this is capital CL, otherwise capital C underscore small l, okay, or say CL alpha 2D, anyways we are giving it a name here 2D. So, I do not think it will trouble us much. So, and then the final plot is about CL naught, right, CL naught, yeah, CL naught 2D instead of, yeah, and X label is alpha at which CL is 0, right, backslash alpha underscore C underscore L, okay. So, let us see, just before doing this I will try to give this input so that I will understand the code is initiated, right. Okay. Yeah. So, this is what CL alpha 3D, how it is varying for different, so if I insert legend here, so say this is, I take it here, so this first data corresponds to backslash alpha underscore D is equals to 3 degree. Okay. So, alpha D is 3 degrees, right. So, the second one corresponds to 4 degrees, right. The third one corresponds to 5 degrees, otherwise backslash DEG backslash, it works, okay. Anyways, fourth one corresponds to 6 degrees if alpha design is at 6 degrees and alpha design is at 7 degrees. So, there are few optimization algorithms in order to achieve these numbers. So, we are not discussing about those algorithms here. So, this is what, no. So, at alpha, say design alpha is at 5 degrees where you are able to achieve the same L by D, right. So, at 5 degrees say, so this is like this green color here. So, that 5 degrees say if your airfoil CL naught or say alpha at which CL is equals to 0 is minus 2 degrees, let us say, right. So, this will be the corresponding CL naught of 2D. So, CL naught of the aerofoil should be 0.067 approximately for that particular case, and then CL alpha 2D should be, so this is per radian. Let us say the design CL is from say 2 degrees, design angle of attack is from 2 degrees to 5 degrees. Okay. So, that means 1, 2, 3, 4, 5, right. So, I am just modifying this, I am just removing 7 degrees trim angle of attack is too high to ask. So, just to make it more realistic, I am trying to remove that particular value. So, okay. You can notice, so for example, in this particular case when you use a symmetric aerofoil, even it demands when you just trim it at 2 degrees alpha, right. So, this is for I can insert the legend here. So, the black is meant for initial alpha trim, which is say if you are trimming at 2 degrees alpha, the CL alpha 3D itself is close to 6.6 radians, 6.2 radians, which is quite high, right, is not it. So, you can say for symmetric aerofoil, say for the same this things trim alpha, for the same trim alpha, which means the data 1 that corresponds to data 1 here, right. So, if I have a cambered aerofoil which has say alpha at which CL is negative, right, at 0.5 minus 0.5 degree. So, then it drops down to say about 5.3, right. You can see this. So, this particular value may be 5, close to 5 here, right. So, yeah, that is 5 per radian for wing. We are talking about 3-dimensional wing. In case of today, it is further more high here, it is more than 8 or 7, which is not realistic, is not it. So, you need to choose a particular value of this alpha at which CL is equals to 0 and then CL alpha 2D, CL naught 2D, right. So, using those values, so from the database, aerofoil database, you will be able to select a particular aerofoil. So, once you select that CL naught and CL alpha 2D and CL alpha 3D, sorry CL naught 2D, you can now go back to this aerofoil database. See here we have presented database of all the NACA aerofoils. So, from theory of wing sections. So, this is based upon that data. So, you can find out what is the CL naught values here for this particular aerofoils, right, and then the CL alpha per radian for this particular aerofoils, and you can also see what is alpha at which CL is 0. So, you can see these values, right. So, you can select based upon this, look considering the corresponding L by D at that particular alpha, right. Okay. Hope you learned something from this exercise. Thank you.